All right, let's go into a little bit more detail with Newton's law of universal gravitation. We established in class that the equation is, as it's seen here, the force due to gravity is a result of a gravitational constant times the product of both masses divided by the radius squared, where we said that the radius is not just the radius separating them, but the distance between the two centers of the objects. In this equation, we can see some important relationships. Because we're looking at products across the top, that means that the force is going to be directly proportional to the mass. If the mass increases, the force will increase directly. So if the mass of one object doubles, the force will double. If the mass of the other object doubles, the force will double. If the mass of both objects doubles, well then double the force, and double the force, you get 4 times the force. That means that the force, Newton's third law says that the force that the first object experiences due to gravity has to be equal and opposite to the force that the second object experiences due to the gravity between the two objects. So that force is going to be directly proportional to the product of both. So as I said before, if we increase the mass of one object, the force will increase proportionally. If we increase the mass of the second object, the force will increase proportionally. If we decrease the mass of both objects, then the force will decrease by the product of the two masses decrease. It's called a direct relationship, and it's directly proportional. The force, as it's shown in this equation, is also inversely proportional to the square of the distance separating the two centers. And this is called an inverse square. And it's very important because there's more than just gravitational force that actually follows an inverse square law. And so it's going to be really good to become familiar with your inverse squares. So it's saying that the force is going to be proportional to the inverse square of the distance of separation. So that means that, say we take this r and we say that this r is just a radius. Right? If we double that radius, and the force is going to be proportional to the inverse square of that radius, if we double the radius, then that radius would be doubled on the bottom, and so that 2 would be squared, and that 2 would be a fourth. And that means that if we double a radius, the force will decrease, or the force will be 1/4 of what it was when the radius was just r. Likewise, if we triple the radius and we plug it in, then you can see that inverse square says that 3r would become a 9r. So that means that compared to the force with just one radius, it's going to be 1/9, or 1/3 squared, is going to be the decrease in the value of the force. So the inverse square law says that as the distance between the two, separating the two objects centers, increases, the force decreases, and the ratio with which the force decreases. The force will decrease when the radius increases, and that relationship is an inverse square. So if the radius becomes 2 radius, then the force becomes 1/4 the force. If the radius becomes 6 radius, then the force will become 1/36 the force. Right, and that's what the inverse square relationship tells us. It also further tells us that if the radius decreases, right, in this case we're not looking at an increase in radius but a decrease in radius. If instead of r we have half of an r, well, half of an r squared would become 0.25, and so that means that the force would increase by a magnitude of 4. So we can add that to our list. If r becomes 0.5 r, then the force would become 4 times the force. That's still an inverse square proportion. Here the radius is decreasing and the force is increasing by a magnitude that is inverse to the square of the radius. This is really nice because it means that when you're doing calculations for force, or if you're looking at a change in force, you don't actually need the magnitudes. You don't need the mass of the two objects, and you don't need the exact number of the radius. You just need the ratio between the first and the second radius. which is really convenient because this makes doing these calculations much faster. So there will be circumstances where you are going to have to actually do some calculations, and when you do, that g, that gravitational constant, has a value of 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. This is convenient because if you're solving for force, the meter squared and the kilogram squared will cancel, giving you newtons. So let's take a look at an example where you and Benny are standing next to each other. We're going to round your mass to about 60 kilograms, and Benny is big today. He has a mass of 260 kilograms, and you can definitely see the size proportion. Now, this is important because it makes you think that, well, if Benny is bigger and he has more mass, then the force of gravity that Benny has might actually be significant enough to feel some sort of a gravitational pull, especially if Benny is nice and close, just over ½ a meter away from you. Well, if we're going to look at the magnitude of gravity between you and Benny, because you have mass and Benny has mass, and therefore you apply a gravitational force to each other, the force that you apply to Benny is toward you, the force that Benny applies to you is toward him, but the size is going to be equal. That's the symmetry that we see in the law. And so we can calculate. All right? We're just going to use our universal gravitation calculation. We're going to plug in 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. We'll call m1 Benny's mass, m2 your mass, and r squared will be the distance between your two centers of 0.682 meters, and then we're going to square that value. When we do, we end up with a force of gravitational attraction between you and Benny that is 2.24 times 10 to the negative 6th newtons. That is approximately 2 millionths of a newton. And remember, a newton is approximately 1 kilogram accelerating at 1 meter per second squared. So let's compare that to the gravity that you experience, or the force of gravity that you experience due to Earth. We know that the force of gravity that you experience due to Earth is equal to mass times gravitational acceleration, so 60 kilograms times 9.8 meters per second squared is going to be 588 newtons. So comparing these numbers, this number is incredibly small and this number is incredibly big. In fact, the ratio is 1 to 4 nanos pieces of a 1. So that's 1 versus 4 times 10 to the negative 9th ratio. So that means that even large objects like a big Benny are too small for us to, in our everyday lives, actually detect or experience, like acknowledge that we experience a gravitational attractive force. But just because those values are incredibly small does not mean that they're not present. In fact, we measured the gravitational attraction between 3 very small objects using very fine equipment, and that's how we actually determined the gravitational constant value, by looking at the acceleration that resulted from 2 very small objects being brought close together and watching how under very magnified conditions we were able to see the motion. So we can also apply this equation or calculation to determine the gravitational attraction of things far from Earth. And so we're going to look at 2 ways to calculate some values that you're going to want to have handy when you're doing this, and then these values would also be provided to you on an equation sheet if you needed them to solve problems. The mass of Earth, 5.98 times 10 to the 24th. The radius between Earth and the surface of Earth is 6.38 times 10 to the 6th meters. And we're going to consider a situation where there is a satellite orbiting around Earth 2 radiuses above the Earth's surface, 2 Earth radiuses above the Earth's surface. So the first thing that we want to consider is that for this object we're going to consider that it's very small and this picture is not to scale. And we're considering the distance separating their 2 centers. So if it's 2 Earth radiuses from the surface, that means there's yet another Earth radius to account for when we're accounting for the total separation. That's going to be a total of 3 Earth's radiuses that we're going to be experiencing. So we could plug this in because we have G, we have the mass of the satellite is 2,000 kilograms, and we have the radius. But that takes time. You're going to have to sit there and plug it in. What if you make errors? So one of the things that you're going to notice is this is a direct proportion, and it's in proportion to an Earth radius, and we happen to know what the acceleration due to gravity is on the surface of the Earth. So let's think about that inverse square law, the proportions that we could use. It's much faster to just use proportions. Okay? Here we know that the satellite is orbiting around the Earth. And we know that that's a result of gravity. And we know that the force of gravity of an object directly on Earth, if this satellite were at the surface of the Earth, then it would be experiencing a weight of mg. Oops, sorry. If this satellite were on the surface, we know it would be experiencing a weight of mg. And mg would equal g m1 m2 over r squared, where one of the m's would be Earth, one of the m's would be the satellite, and the radius would just be this one r right here. Well, this one is experiencing a radius of 3r, and 3r is a proportion. So that means that if instead of plugging 1 Earth radius down there and using 9.8 there, if we plugged in 3 r's instead, then we know that the force is inversely proportional to 1 over r squared. So when we plug that in, we're going to plug in the 3r, and we know that the difference between the two is going to be a 9, or the force that this satellite is experiencing is 1/9 the force it would experience if it were on the surface. So that means that we could compare the force, which on the surface of the Earth would be mg, is now 1/9 of mg. And that means that we know mg is going to be 2,000 kilograms times 9.8 meters per second. We take 1/9 of that, and we end up with an actual value. That was much faster than calculating. But if you did plug in g, m1, m2, and r squared, you would end up getting the same answer. So this is a faster way to solve when you're just comparing ratios or proportions. Let's take a more detailed look at a situation where we want to look at the force that the moon is experiencing as a result of being at a 90 degree to the sun and to the Earth. And so I might just need to pull up some numbers real quick. So we'll let this focus, and I'm going to get my numbers. Alright, so we know that in this situation, the moon should experience a gravitational force from the moon to the Earth, and we should also experience a gravitational force from the moon to the sun, and each of those forces should be a gravitational force that's a proportion of the total force. So putting that into our free body diagram, we're breaking that down by values that are easy to measure and calculate. That means that our moon is experiencing the force of gravity to Earth, and our moon is experiencing the force of gravity to the sun. And that means that the net force that the moon is experiencing is going to be somewhere in here, the sum of those two forces added vectorially. Lucky for us, we're looking at a situation where it's a 90 degree, so that means that the net force is going to be resolved according to Pythagorean's theorem. The net force will be equal to the square root of the force from Earth's gravity squared plus the force of Sun's gravity squared. So that means that in order for us to find that value, we're only going to need to figure out the force of gravity between the moon and the Earth, and the force of gravity between the moon and the sun. So we're going to need to know the mass of the Earth, the mass of the Sun, the mass of the Moon, the separation between the Moon and the Earth centers, and the separation between the Moon and the Sun center. So let's go ahead and start putting those down. We're going to say the mass of the Earth is 5.98 times 10 to the 24th kilograms. The mass of the Moon is going to be, this is one I don't have memorized, 7.35 times 10 to the 22nd kilograms. The mass of the Sun is going to be 1.99 times 10 to the 30th kilograms. The radius between the Earth and the Moon is a value of 3.84 times 10 to the 8th. And the radius between the Moon and the Sun is going to be a value of 1.50 times 10 to the 11th. So we're going to have two forces. This is going to be the force from the Sun, and that's going to be G, and it's going to be the mass of the Moon times the mass of the Sun divided by the radius between the Moon and the Sun squared. The force from the Earth is going to be G, mass of the Moon, mass of the Earth, divided by the radius between the Earth and the Moon squared. Now, I could plug those in for you, but this is straight calculation, so I'm going to go ahead and I'm going to have you plug in the numbers, and the value that you should get should be 1.99 times 10 to the 20th newtons for the force of gravity from the Earth. And for the force from the gravity from Sun, it should be 4.39 times 10 to the 20th newtons. So now we can apply Pythagorean's theorem to these numbers to find our total net force, and that's going to be 1.99 times 10 to the 20th squared plus 4.39 times 10 to the 20th squared. Square root that, and you're going to get a net force of 4.77 times 10 to the 20th newtons. And that force has an angle. If we do our tip to tail method, then it's going to be Sun over Earth for our, tip to tail. Earth over Sun. So that means that theta is going to be equal to the inverse tangent of 1.99 divided by 4.39. Here I've left off the exponent 10 to the 20th because they'd cancel out top and bottom. And our angle here would actually be 24.6 degrees. So that means that in the Moon's orbit around Earth, when the Earth and the Sun are at 90 degrees to the Moon, that means that the Moon actually does not have a net force pointing directly to the center. The Moon would have a force tangential, and a radial acceleration. So that means that the Moon would actually speed up at this point in its orbit. The last thing that we're going to take a look at in this lecture is we're going to look at gravity near the Earth's surface. A few things that we know. We know that when the net force is mass times gravity, or when we're looking at the weight of an object, it equals mg. We can also solve for a gravitational attraction using Newton's universal law of gravity. In fact, the answer to this and the answer to this, assuming that this is talking about on the Earth's surface, would give you the exact same amount. So that means that in the situation at the surface of the Earth, mg is going to be equal to Newton's universal law of gravitation. And this means that one thing becomes true. You can cancel in this equation the mass that's the same on both sides, and that means that g, the acceleration due to gravity, is going to be equal to the universal gravitational constant times the ratio of the mass of Earth to the radius of the Earth. So that also means that if you know the mass of Earth, then you can determine how acceleration will change, acceleration due to gravity, depending on, oh, and that should have a square down there, I'm so sorry, depending on how far away from Earth's surface you are, which means that, say, for example, you dug down until you were halfway to the core, that means that the acceleration due to gravity at that point should actually be 4 times greater than the acceleration due to gravity that you experience on the surface. Whereas if you were launched into space and you were orbiting 1 Earth radius above the surface, then that would mean that you were 2 Earth's radius from the center, and your gravity would be 1/4, your acceleration due to gravity would be 1/4 of the acceleration due to gravity that you would experience on the surface. One thing that I want to point out to you that's incredibly important is that the big G and the little g are related to one another, yet they are not interchangeable and they're not the same value. The big G is a gravitational constant. It's a constant and it shows the relationship between the mass and the radius and Earth's force. It is an incredibly small number because that relationship, or that force that any mass can apply to gravity, is very small, but increases with increasing radius, or increases with decreasing radius. So inverse square law again, and it's for 2 different objects, so you have 2 masses in there. The value is 6.67 times 10 to the negative 11th. The units are completely different. This is not an acceleration, it is a constant that shows a relationship. G, little g, on the other hand, is the acceleration due to gravity on Earth's surface. It is an acceleration. It has the units meters per second squared, and it is the value 9.8 meters per second squared. So do not get them mixed up. Make sure that you are using them each accordingly. So a few things that we should be able to accept now is that if you know the acceleration due to gravity on Earth's surface, and you know Earth's radius, and Earth's radius is actually found due to sound data and earthquake data, was how we were able to calculate Earth's radius. But if you know these two, just as we knew these two a long time ago, you can actually use Newton's universal gravitational constant to calculate the mass of the Earth. And this is how we measured Earth's mass. You can't take Earth, which is floating non-directionally in space, and you can't even say that it's floating because relative to what? It's impossible to know, but you can't put Earth on a giant mass balance, which means that this is how we were able to determine the mass of the Earth, and it wasn't until we had the gravitational constant that we were able to calculate Earth's mass. And it can be done for other planets as well, so this is how we can determine in other circumstances the mass of other planets, as long as we could ascertain or discern the acceleration due to gravity at the radius and the mass of another object. So that means that as long as we have 2 of these 3, we can determine any other one value for another planet, which is really kind of cool because it's definitely the direct connection between the fundamental laws of dynamics that we've been studying in the class and how it relates to the terrestrial movement of the planets and the astronomical data that we observe out in space.